welcome to our lab this week where we're going to determine the empirical formula of a copper chloride compound. First, let's review a couple of terms, and I know in my lecture we've already talked about this, but let's go over it again real quick. Molecular formula shows how many of each type of atom is in an actual molecule. For example, glucose contains 6 carbons, 12 hydrogens, and 6 oxygens. 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen. The empirical formula shows the smallest whole number ratio of atoms present in a molecule. So if we take glucose again, which has a molecular formula of C6H12O6, its empirical formula is CH2O. And you'll see today it's much easier to determine an empirical formula, and that's why we would even care about this empirical formula. So what do we end up doing? We do something in the lab and we get mass percent data, and then we do some work with pen and paper to turn that into an empirical formula. The mass percent data is a mass to mass ratio, while the empirical formula represents a mole to mole ratio. In analysis labs, we try to determine the empirical formula of an unknown compound. So for example, if we have a compound that we know contains some amount of carbon and some amount of hydrogen, we would burn that. We would burn that compound, known as a hydrocarbon, in excess oxygen. And then we would be able to determine by collecting and weighing the amount of CO2 and H2O that's formed. Where in this reaction, all of the carbon comes from the hydrocarbon and all of the hydrogen comes from the hydrocarbon. So from the amount of CO2 collected, we can get the percent by mass of carbon in the sample, number of carbon atoms in the empirical formula. From the amount of H2O collected, we can get percent mass hydrogen in the sample and figure out the number of hydrogen atoms in the empirical formula. What are we actually doing in today's lab? We're taking zinc and we're using zinc to perform a reduction reaction where zinc reacts with our copper chloride compound to form zinc chloride and copper. And what we see here is just similar to the combustion reaction. All of the copper that we get at the end comes from the copper chloride compound. So we're going to be able to work back and figure out percent by mass of copper in this compound. Here's a few things, and I'll say this a couple of times. Do not weigh the copper chloride solution. We've made the concentration of the copper chloride solution so that 25.00 mLs of the solution contains exactly 2.017 grams of copper chloride. You're going to start with a zinc rod. We've set this up for you so that the zinc rod, which you will weigh, the zinc will be in excess. The copper chloride solution will be the limiting reagent, and the zinc chloride is very soluble in water. It stays in solution, and the copper metal will precipitate from the solution. Okay, so what you're going to do is you're going to weigh your zinc rod at the beginning, and finally you're also going to collect, dry, and weigh the copper that's present at the end. From this, you'll be able to figure out what X and Y are in this expression. Also, I want to point out that the zinc is the excess reagent in this reaction. We've intentionally given you more than enough zinc, so you're going to react with all the copper. Copper is the limiting reagent. Here's sort of what it's going to look like. You're going to use a zinc rod, kind of a pencil-shaped piece of zinc. I'm showing here with this zinc plate instead because I think it's easier to see. We have at the beginning of the reaction this nice shiny, what we're used to for a metal, nice shiny piece of metal. We put it into this copper containing solution, and very quickly we get a plating out here of solid copper. And I'll mention this as we go through, but so this eventually blocks the surface of the zinc where the reaction is taking place. So you guys will want to carefully take your rubber policeman and sweep off this surface, let this copper drop to the bottom, and give you more reactive surface. That'll also speed up your reaction. So ultimately, you will calculate the mass of the copper that's formed, the mass of the zinc that got used up, and from this, you can determine the empirical formula for the copper compound. And here's some experimental tips. Use the zinc rod, scrape it to get a shiny surface. We've actually, at this point, we've provided you with sandpaper. You can use sandpaper to remove the zinc oxide that's on the surface and give a shiny and very reactive surface by doing this right before the experiment. After scraping, you want to weigh to 3 decimal places and record that weight. Your zinc rod must weigh more than 1 gram. Okay? That's in order to ensure that it will be the excess reagent. We want to have more than enough zinc there. Each pair will take about 60 mLs of copper solution in a 100 milliliter beaker. You'll use a graduated pipette, volumetric pipette to pull this out, and that's how we know we're going to get exactly 25.00 mLs of the solution. This solution will contain 2.017 grams of copper chloride and 25.00 mLs of the solution. Okay, when you have judged that you're done, at the end you'll want to allow about 2 minutes for all the copper in the solution to settle out. I can't stress this one enough. Don't scrape the zinc rod too aggressively. You definitely don't want to use a piece of metal to scrape it or the rubber policeman too aggressively, because you will scrape out some of the zinc. You want the zinc to stay put on the zinc rod, and you want the copper to come off. You want to dry your copper thoroughly. Get the evaporating dish heating early. You can stop weighing when 2 weighings are the same to 3 decimal places. You'll heat the copper, take it out, let it cool, weigh it, heat the copper again, take it out, let it cool until the weight agrees to 3 decimal places. You'll want to use tongs and wire gauze to carry the copper samples to the balance. Here's a few hints for doing calculations. Use your empirical formula for the copper chloride to balance the equation. So you'll put in whatever you figured out for x and y in here and balance this equation. The definition of the theoretical yield is the amount of product that would form if all of the limiting reagent was used. And you'll start, again, now we're giving you 2.017 grams of the copper chloride. And you will want to figure out, using your formula, what's the molar mass according to your formula. And then from the balanced equation, you want to have the ratio of moles of the copper chloride to moles of copper that are formed. This gives the maximum mass of copper that could be produced from 2.017 grams of copper chloride. All right, going to go through and cancel our units now. We would have grams on the bottom, canceling grams, moles canceling moles, and then finally moles of copper canceling moles of copper. And from this we would predict how many grams of copper we would expect from 2.017 grams of copper chloride. All right, percent yield. So percent yield is the actual yield of copper in grams divided by the theoretical yield. So the theoretical yield is the absolute best. If the reaction was run perfectly and everything was recovered perfectly, how much you would get. Actual yield is what you actually got. So maybe you spilled some, maybe the reaction didn't quite run long enough. And so we expect in general to have percent yields that are less than 100. So you've lost some amount. Right, we might have 90% yield, might have 95% yield, we might have 40% yield. We expect this to be less than 100%. The only times when it really isn't is when we have something in there that shouldn't be there, and very often that's water. If your actual yield is over your theoretical yield, very, very often we have the compound isn't dry, and so your actual yield is your actual yield plus whatever water is adhering to your copper. And so this can make the actual yield look higher than the theoretical yield, and you would report a percent yield that's higher than 100%. All right, you're going to be asked to answer a few questions. For example, is the experimental mass percent copper too high or too low if X, Y, or Z is done? Is the experimental mass percent chloride too high or too low, and why for each of those? The thing you want to think about here as you're doing this, for many of these, what happens is since you're only really measuring copper and you're not measuring chloride, is if for some reason you calculate too much copper, that's always going to make the chlorine look too low, and too little copper will make it look too high. Again, because we're only really working with one of them, the copper, it will make the other one look whichever way. Okay, if the copper is too high, then the chlorine will be too low. If the copper is too low, the chlorine will look too high. All right, I want to talk a bit about pipetting techniques, because we do have some danger here when we're using the pipette. So the pipette is a long hollow glass rod, and what you most certainly don't want to do is ever have basically your hands too far apart on this. The reason is, if I took this hand here and left it where it's at and took this hand way down to the bottom, any force that I apply has quite a bit of torque to it, and it's easy to snap this. If we snap the neck, it's very easy for us to cut ourselves at the point that we do break it. What we want to do is, in general, keep our hands pretty close together. You will use a different type of bulb than this, but basically the idea is going to be the same. I describe it as you almost want this bulb to just sort of kiss the top of this. You most certainly do not want to try to jam it in. It's not designed to do that, and that's one of the ways of breaking it and then cutting yourself as you break it. So you want it basically to just sort of kiss the top. This dashed line marks where you're eventually the calibrated line that you're trying to get to. So what you do is you use this mechanical suction device. You always want to use it to pull some amount above the line. So look, we've got it above the line here. You can then use a piece of paper towel or something to dab off any that's on the outside. And then what you can do is slowly release your finger here to allow it to drip, drip, drip through, just like you might do it with a straw at a restaurant, until you get exactly to the line. And then you can take it over to your where you want to deliver it, remove your finger completely and let it drop. You want it to let it drip out all the way, but not to push. These are designed to retain about one drop in the end. You don't want to use your finger to try to tap and make that drop come through or anything like that. You just want it to naturally let it drain and then leave about one drop in the tip, and that's how it's designed to be. So here's some of those admonitions. Do not jam the pipette pump onto the pipette. Do not draw liquid into the pipette pump, so you don't want to go so high that you get it up into the pump. That just makes a mess. And do not blow out the liquid from the pipette tip. This also is showing you you want the meniscus, so the bottom of this curve, to be right on the line. You want to be level with the line when you're looking at it. And you would have had the liquid somewhere up here above it, drip, 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 until you get to you're happy and you got it right at the line. Then you transfer it over to where you want it to be and let it all come out and leave that one drip and that one drop in the end. All right, here's some tips and tricks. Each person does one trial. Lab partners work on their trials at the same time. So you and your partner together will have 2 trials, with each of you running your own trial side by side. Don't pipette directly out of the stock solution bottle that comes from the stock room. You will use a 25.00 ml pipette to measure the copper chloride solution, and not a 50 ml graduated cylinder. It's not accurate enough. You'll use sandpaper to give the zinc rod a shiny surface, and then weigh the zinc rod to make sure that it's above 1 gram. There are exactly 2.017 grams of copper chloride in 25.00 mLs of the solution. Hot plate settings. You want to set it in the 150 to 200 degrees C range, or about a setting of 3 on most of the hot plates. If you get this too hot, you can oxidize the copper. The evaporating dish must be cool before weighing. You will want to use all of the digits on the balance, for example 0.001. You may need to put on the balance cover to minimize air currents, and you want to avoid leaning on the workbenches because that will make the mass go up and down. You want to use the same balance while weighing the copper to determine if it's dry. Reading should agree to at least 0.01. to be consistent. Okay, 0.01, not 0.001. So to the second decimal place, they need to be consistent. This is procedure step 34. And use tongs, not test tube clamps. You can ask me, or you can ask your lab instructor if you're confused about this, and wire gauze to carry your evaporating dishes to the balance. All right, all the waste for this lab needs to go into the appropriate waste containers. You need to have your full safety equipment for this lab.